come this far, we want to use the data that we have instead of actually using this to project the points all the way to the surface. We can use that as a direction for a raycast, which will give us more accurate results for our closest points on the surface. So we are going to use a raycast node. Okay. Now, the raycast node takes geometry, which is our torus. It takes position, which is get point positions. We'll just duplicate this, keep things from getting too cluttered with lines going everywhere. And it also takes a direction. Now the direction is the is going to be these vectors, but we don't want to actually use the entire vector. We just need the direction from it. So we're going to use a normalized node. And then if you visualize this, you'll see all of your vectors go to unit length, which is 1, and that is better to use with the raycast, just to keep things from being extended, and that causes problems later on down the road. So we'll use that as the direction, and again, that gives us a location. So we fixed that problem before. To fix that, we use a get data. Use that as a source, and then double click our get data, and we want the point position from that data. I don't know why this is still a hand. Okay, now let's see the results of that operation. Woo, that is not right. And the problem with that is that we need to take that data and we need to subtract from this the point positions, because right now there's like a doubling effect of it's adding the point position to the results of our raycast, and that's giving us results that are elongated and abnormal. So what we wanted to do, I know this is extremely hard to see, so I'm just going to do some cleanup real quick. Grab all this and move it back here. Alright, that gives us something better to look at. Again, I apologize for this monitor. The screen is small. Yes, we need to copy this get point position, and you can use the same get point position for the get closest location and the raycast, but I just like to use different ones because it gets hard for me to tell what's going on after a while. If I have a whole bunch of lines going around, it looks like spaghetti code. But we want to subtract. I'm gonna open up my panel here. Get a subtract node. Of course, I could just duplicate it. Didn't think about it. And we want to take our original point positions out of our raycast. And when we do that, we should have the correct values, and we do. Alright, so if we go in here and start moving this guy around, you see that if you keep an eye on this area, you'll see that they're actually moving around the actual surface. They're still kind of favoring the edges, but it's more freedom and range of movement, and it's also not popping in this area anymore. Well, once it gets to a certain range, because the positions change suddenly, or it goes inside the geometry, but as a whole, it just moves around a lot smoother. So now that we have this data, we want to apply our deformation, and it's not as simple as going straight from here to a set data to setting our point position. I guess I'll show you that. If you go straight from here to setting the point position with a set data, pipe that into the value and explore, and to torus, polygon mesh, point position, and pipe that into there, you'll see that absolutely nothing is happening because I put that on torus, and that's supposed to be grid. You'll see that everything is all messed up, and the reason that is similar to the operation that we had to do of subtracting the point position of the grid from the point positions of the closest location, because there's like a doubling effect, and to get rid of that effect we need to do a little additional math. Okay, so the additional math that I use is from here we need another get point position, and we also need to need an add node. I think I said you need to subtract earlier, but you need to add to get the deformation to look right. So you want to add the point position to the results of the retcast after the subtract and everything. And then if we use that for our, and then go there. Oops. If we use that to set the grid's position, it should set to the correct place. Ooh. Ah, okay. And there it is. It's going to the place where our visualization is. Exactly. So pipe in the execute, and you'll see that it's there. And you can, you can take that and move it around, and it stays there. You can go in and start adding points, and it'll follow the geometry of your torus, and you can use that for simple retopology. And it's just a demonstration of what you can do with a few simple adds, subtracts, and recasts. And oh yes, there's one more thing I want to show you. So we have this, and it'd be cool to have a way to control the offset of how close our rays are to our torus. So in order to do that, we go back to our operation after the subtract on the raycast. And in order to change the length of a vector, you multiply it. Now, multiplication of a vector is the same as scaling a vector. So you want to multiply. You want to multiply by scalar, actually, because we're going to use a variable to control the amount that we are projecting. So if you is it why isn't that going 3, 1, oops. Let's try this one. this is the correct place. But I forgot to put it in my visualization, of course. Go in there. Alright, let's go back to 1. Now, so you move this, and that's how you scale the vectors away. Now, the problem is, if we go too far, it actually goes through our geometry, and we don't want that. So what we want to do is we want to create a scalar node, and we want to create a rescale. And our rescale is what's going to keep our node, our scalar node, from being from going past 1. And we're going to rescale to 1. Oh, but 1 is kind of small because, you know, you want to have more range of motion here. And in order to get the range, we're going to use 10. So we're just going to do a simple divide by scalar, and we're going to divide by 10. Pretty simple. And that gives us to where we can have our scalar going from 1 to 10, which is the default maximum for scalars, which is convenient. And so we can pipe that back into our tree, and if you move your scalar, it conforms to the surface. Alright, I hope this has been helpful. It took me a while to figure out, but once I figured it out, I was like, wow, this is really simple. And hopefully you guys can either use this or take it and extend upon it, and give me some feedback on the tutorial if you liked it. Tell me you liked it. If you didn't, tell me I suck. But thanks for your time, and thanks for watching.